Recording. Ta-da. There. It's back. Just interrupt it. There. Sorry for the technical difficulties. So let's see, what other? Inclusive OR. Inclusive OR. So a bitwise inclusive OR looks like this. What does a logical inclusive OR look like? Two, yes, that's two of them. So A, logical, or B. Yes, sir.
Is this supposed to be like a single line or two dots?
Two dots?
Or two dashes, I guess.
Two dashes like this?
No,
up and down.
You have two
For the bits
on the sheet, it looks like just a single line from top to bottom.
Yeah, the machine's typography is defective. I think if you look at the keystrokes, you'll see that it comes out as two dashes vertically. If you have,
Yeah, I got it.
when you have it there, does it look that way? Yeah, and how do you type that? Here it is. It's above the backslash. So above the backslash, it looks like a.
The button above enter.
Is it the button above enter?
Well, but it's on the same key.
No. It's on the same key as backslash.
Yeah.
The button above enter is a backslash.
Yeah.
So backslash is ASCII code 92. In case you're wondering. So this is. Suppose you wanted to do a bitwise negation, A tilde. How would you do a Boolean negation? Exclamation point. This, by the way, works in C and C++ and in Java, and C# for that matter, as well as other languages. Suppose you wanted to say, A exclusive OR B. A exclusive OR B. How would you do that in Boolean land? Boolean land. Let's see what A exclusive OR B does. A and B. Am I on the screen? Yes. 0001 1011. A exclusive OR B 0110. If A equals B, the output is 0. If A is both 1, A equals B, output is 0. If A is not equal to B, the output is 1. So this is the equivalent of A not equal to B. How do you do that in the Boolean algebra implemented in the Arduino? Not equal.
Exclamation equal.
Yeah, exclamation equal. So A is not equal to B. That's what A exclusive OR B ends up doing when you look at the truth table. A is not equal to B. Yes, sir.
So the right hand side describes the whatever language you use in Arduino.
Logical.
Okay, so it describes logic in Arduino. On the left hand side, what does that describe? Is it just operational or is it another language?
It's the same language.
So both of them are synonymous. You could use.
They're both operational. You can type this stuff into your Arduino, Java, C++, C, or C# code. This works.
So you can use both the right hand and the left hand in Arduino, C, or anything.
Well, all the languages that we studied here at the university that I know of.
Okay.
One of them you perform on bits and the other one you perform on a
Yeah.
scalar. like a-
Input to this
or an
is
integer.
Boolean data type.
Okay.
Output is Boolean. Input to this is scalar data type. Output is scalar. Yes, sir.
Can you use these on, like any, like, use them on bytes and bits, or is it?
Yeah, and you can use them on this, the bitwise you can use on any scalar data type. 8, 16, 32, and 64 represent byte, int, well, actually shorts, int, and long. So, let me clean up my slop. Shorts, byte and shorts. So, oh, and char. It'll work on char. So in the world of Java, these bitwise operations work on that. And by the way, you can find these kinds of things available in Arduino as well.
So you can do a bitwise operation on a car array, pair array?
Yes, you can.
Is it gonna do it via the ASCII, or is it gonna be just something else?
If you are in an ASCII-based system, it will give you an ASCII-based result.
Mm.
If you are in a non-ASCII-based system, it will give you a non-ASCII-based result. So if you're using Unicode and your underlying character set is katakana, and you're doing it in Japanese, you're going to get some sort of Japanese result. But if you're using ASCII and you clear one of the bits, you can change lowercase to uppercase using ASCII because it's very symmetric that way. The difference between the lowercase a and the uppercase a is one of the bits is set. So you can proceed to lowercase things quite efficiently using bitwise operations in ASCII.
Okay.
So this is a, an interesting point. Sometimes people do efficient, clever things with these bitwise operations that give you results which are not obvious to the casual reader. And sometimes I rail against the clever code. I say, you shouldn't be so clever. But on the other hand, it's very efficient. So it's a trade-off. Any other questions? Yes, sir.
I'm a little confused about the mask, question 2. The mask.
Oh, well, any questions about this? So now we've got the answer to this one. Okay, let's do question 2. To perform a bitwise mask, use ampersand, that is, and then it says, is it true or false? Well, what do we know about bitwise mask? We know that if we want to do it bitwise, we don't use ampersand, that's logical. You have to use a single ampersand. So what we know is this is not true. This is false. I mean, you can take it for granted that if he's asking for bitwise and he says, does this work? The answer is no, you need this, not that.
So what's the other one do?
Well, it throws a syntax error.
Okay.
In Java, it doesn't work because what your output is Boolean, and what you're trying to do is you're trying to assign it to a byte. So if you said something that's of type byte is going to now be equal to something that's of type Boolean, the compiler will get its panties in a twist or something. It'll say, this is an illegal type assignment. And you could try and cast it and see if that'll work, but I don't think so. Because how do you convert from byte to Boolean?
Right.
It doesn't know how to do that. Yes.
There's some functions built into Java that return bytes when you're given, when you like pass arguments that are Boolean and stuff.
You can write a function that will input one thing and return something else. Like, for example, you could compare apples and oranges and say, are they equal? Or is the apple greater than an orange? And what do? Well, maybe you decide it's greater because it's got more fiber. Maybe you decide it's greater because it has less sugar. Or maybe you decide it's greater because it's got fewer calories. I don't know. So if you want to write a function that compares apples and oranges and decide, well, gee, I can compare them any one of a number of ways, you can always return true and false or greater than or less than. It's perfectly valid. You compare objects this way with interesting functions that you write yourself. And then you can have a generalized sorting algorithm which takes comparable things. They implement the comparable interface using whatever thing you want to use for comparison, and then sorts the list. So you might say, I'm going to screen 5,000 stocks in the stock market using the comparable intrinsic value of Warren Buffett. So you implement comparable using intrinsic value, and then you sort by intrinsic value, which is different from market cap and actual price. And then you can say, this is the most intrinsically valuable stock given whatever. And you have your own way to compare these various things. So yeah, you can definitely do that. You can write a program, you can write a function to compare and return Booleans given any argument you like. Number 6. This is the shifting thing. I think we kind of went through a lot of this in the last lecture, but that's all right.
Yes.
We'll do it again. So assume B is of type byte. So B equals B shift 1. Will this give the same numerical result as B equals B divided by 2? In case you had any question at all about this, let's do a sample. Let B equal 4, base 10. That means B is equal to 1, 0, 0. Now let's shift it over by 1 bit. Now I have 1, 0. If this is the binary for 4, then this must be the binary for 2. Right? And so now what I have is a way to show you, yes, indeed, shifting to the right by 1 is the same thing in binary as dividing by 2. This is, by the way, division by an integer. So what he's doing there is he's going to divide by a fixed point quantity and give you a fixed point quantity. So what will happen, what happens if the input isn't 2? What happens if the input is 3? And you divide by 2 using integer division. The result will be 1. The whole number of times that 2 goes into 3. Right? If you want the remainder, then you need the mod operation. Yes, sir.
So the B greater than 1 and B divided by 2, are those the same operator or are they different?
They give you the same result. They are different operators. And the reason why is because if you want, you could shift over by 10 or 11. But if you wanted to do that, then you would have to divide through by 2 to the 11. And division, generally speaking, takes more CPU cycles than shifting. A barrel shifter will be able to do the shift operation in one CPU cycle. Whereas a division like this could take several cycles. What do you think of that? I used to program a microprocessor called the 68000. It was built into the Mac Plus. It took 154 cycles to do an unsigned integer multiply. And 154 cycles at 8 megahertz for that machine meant you couldn't do it faster than 8 megahertz divided by 154 clock cycles. That's how fast it would run. And so you had to take that into account when you were attempting to do real-time control or filtering. So sometimes it takes a little while to do those more extensive operations. Any other questions about this homework? Yes?
Can I do question 12?
Question 12. Sure. When an LED has 7/10 of a volt drop in voltage, I guess that's redundant. When an LED has 0.7 volts DC drop in voltage and 5 volts is applied, why put a 220 ohm resistor in series? Does it limit the current to 2 over 220, which equals 9 milliamps?
True.
You know, I said it was true, but my question is, why would it be 2 over 220? Where did I get that number?
I think if you do the math, it's supposed to be 5 over 220 because you're applying 5 volts.
Yeah, I wonder if I got a typo there. That's 5 over 220.
5 over 220 is not equal to 9 milliamps, but 2 over 220 does.
Right. Shouldn't it be more like 7.7 minus 5 divided by 220?
Yeah, so it's supposed to be 4.3.
It should be. Oh, there's a bug. Okay, so there's a bug. But if you've already done it, I can't really correct it. So anyway, it's 5 minus the voltage drop, which is probably 4.3, divided by 220 ohms.
19.5 milliamps.
What kind of number did you get?
19.5.
19 and a half?
Milliamps.
Can we call it 20 milliamps?
Twice as much.
Yeah, well, it says 9 milliamps here. Yeah, this is a bug. I've got a bug in my answer key. You know what you could do is I could change it to, I see if I change it to false, then everybody who's done it already will get it wrong. This needs to be fixed. I will fix it. Don't worry, I'll fix it. See, a number of people have already taken this homework, and they probably adapted to getting the wrong answer and figured out how to get the right answer, but then they didn't know why it was the right answer because it's really a bug.
So
in my homework.
your answer was true.
My answer key says true, but it's obviously not true. So what I'll do is I will fix it when I get home.
Are you gonna fix the
I'll
answer?
probably make it so that nobody loses credit somehow. I think there's a way to do it in Blackboard. I don't quite know what it is off the top of my head, and I'm not going to waste class time figuring it out because it's not nice. So
Can we do
put it in my
number
pocket. I'll
7?
take it out when I get home. Yes.
Can we do number 7?
Number 7. I think I just stuffed it in my pocket. Oh, here it is. Number 7, left shift. Byte B equals 4, and then B is set equal to shift. Oh no, B equals left shift 2. Left shift 1. Isn't the value of B now 8? This looks like a bug too. Wait a minute. I think it's supposed to say B equals B left shift 2. Let's just make sure that's right. Did this come out so buggy? I don't remember this being buggy last year. I wonder if the copying did some nonsense. Oh, I see. B equals 4. B equal left shift 2 is the same as B equals B left shift 2. And the reason why is the same reason why you can use C B++. You know, if you put operators next to one another, greater than equal, things like that, it treats it as a single operator. So by doing equal less than, what it's doing is it's doing B equals B shift 2. So it's taking 4, 1, 0, 0, and then shifting in 2 zeros to the right, shifting it over to the left, and now what do we get?
16.
Yeah, what's it? Well, no, 32, I think, isn't it? No, you're right, 16. And I'm looking for the next side to this page, which I think I stuffed in my pocket. This is page 5. I'm looking for page 5. No, that's stuffed in my pocket. I'll find it. Page 5. Here's page 5. Yeah, false. 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 It is 16 because shift 2 is the same as B equals B times 4. Right? So this is the same as B equals B times 4. That's like multiplying by 2 to the 4. I'm sorry, 2 to the 2, which is 4.
So what does the shift do? Just
It moves the numbers.
So right, but operationally, as in mathematically, what would it do?
Well, this is equivalent to B equals B times 2 to the 2, which equals B times 4.
So if it was shift 4, I mean, that was 4, yeah.
Then it would be, it'd be the same as 2 to the 4, which is 16.
So you're just changing the power of 4.
This is always using powers of 2 because the underlying representation is binary.
I see. Thank you.
Yeah, sure. Any other questions? Number 9. So you need page 6. Page 6. Okay, there's a little bit of a typo. There should be a space between uno and uses. So it's supposed to say the Arduino Uno uses the AT Mega 328P processor. And the answer to that is yes, it does. And you can Google these things too if you want, but it's also in the book. So there's a couple of ways you can do it. You could look at your Arduino and look at the chip, and it says 328P right on it. So that's a way to go if you want to, get the answer to these things. It's not that hard, I think. I'm going to save this for later so I can fix it. So I see there's a typo. Anything else? Wow, we really ran through that homework pretty good. Let's take a look at homework number 2. Homework number 2 is really about programming the Arduino. And when we're doing the programming, we're programming in C++. So Arduino programming is equivalent to C++ programming, but the underlying hardware of the Arduino is one of the things that we need to keep in mind when we do this kind of programming. And I'll make this homework 2 available to you a little bit later on in the week, because right now we should be focused on homework 1. So there's a thing that we use for serial communication called the baud rate. Baud rate. Why do we use baud rate? Or maybe more to the point, what is the baud rate? What does that mean? So, I beg your pardon? It refers to the symbol, the number of symbols per second. Symbols per second. If you have only 2 symbols, 0 and 1, then it's equivalent to the bit rate, the number of bits per second. If, and only if, the number of symbols is equal to 2. Does the number of symbols have to be 2? The answer is no. Why not? Well, because sometimes when you do digital data communications, you modulate for the channel using a constellation that's based in phase and in frequency. And when you send a symbol, you select different phases and different frequencies. And your maximum a posteriori receiver, also known as the map receiver, has a series of filters, which is able to determine when these symbols are being sent. And you can imagine it's just like a touch-tone phone where you send different numbers that have a dual-tone multiple frequency system associated with it. As many of these as you like, as many as can be efficiently discriminated against. Maybe there's more. So if I have 16 symbols, then each symbol, if they're all equally probable, is worth log to the base 2 of 16, which is equal to 4 bits, because 2 to the 4 is equal to 16. So you're getting 4 bits per symbol. So if I send you 10 symbols per second, your equivalent bit rate is actually 4 times that, or 40 bits per second. So bit rate and baud rate are different. They don't have to be, but in general, it's not equal to the bit rate. It's equal to the number of symbols per second. And if you know how many bits you can get per symbol, then you can know how many bits equivalent you're going to be transmitting per second. Why do they call it the baud rate? Where'd that name come from?
Just come from the both plot of the frequencies they use.
Comes from the what now?
Oh, sorry.
So the baud, is that what you said, the baud? Yeah,
Sorry, yeah, that's what
it comes from baud. So baudots are actually a code that people were using, and it's named after Jean-Maurice Emile Baudot. Baudot. And he's a French telegraph engineer who lived from 1845 to 1903. And he created a Baudot code, and he's a telecommunications pioneer. And so they named the baud unit after him. When you have something that's named after a person, that has a special word associated with it. They call it an eponym. So if you have Einsteinian notations named after Einstein, that's an eponym. That's a good Scrabble word, by the way, in case you need Scrabble words. Let's see now. So baud rate is not equal to the bit rate. It's equal to the symbol rate. That's important. Actually, that's the answer to question number 1 in homework number 2 for your lecture homework. Serial communications is very important for microcontrollers because they need to have a way to talk to the sensors and to talk to other computers. So for example, when you plug in the USB interface of your Arduino into your USB port on your computer, it's using a serial communication protocol. And in fact, what it's doing is it's simulating a serial port that uses what's known as asynchronous communications. And it's kind of important for us to learn about these things because practically everybody's using things like USB, and Thunderbolt, and Firewire, and I2C, and SPI, and serial communications, high-speed serial communications are actually very efficient ways for us in which to interconnect peripherals. So let's think about synchronous. O-N-O-U-S. S-Y-N-C-H-R. Synchronous. Where's the C? Yeah, Chronos. So that's got Chronos in it. There you go, Chronos. So what does synchronous mean? Synchronous. Yes.
At the same time? Or?
In time. Yeah. In time. And what is who is Chronos?
The god of time.
Greek god of time. And who was the Egyptian god of time?
Horus.
Horus, right? So when you go to Whaley Avenue in New Haven, you can find a person who is in a store named horologists. Horologists are your clock makers. We don't call them chronologists. That sounds like something different. So synchronous means it's in time. And of course, if you put the term asynchronous next to it, it means it's out of time. When you have a serial communication protocol, you can have a transmit line, you can have a receive line. The transmit line will transmit binary data, and the receive line will receive it. And that's clear. But if you want it to be synchronous, then you're going to have a transmit clock, and you're going to have a receive clock. And if you have synchronicity in those clock signals, you can run at much higher speeds. But an asynchronous system will try to embed the clock signals directly into the transmit and receive lines. So these transmit and receive signals are often distinguished from the data that you want to transmit. So you have a kind of overhead, right? We'll call this the start bit. This is what's known as a framing bit because it allows you to determine when the signal is going to begin. Then you have a series of pulses. It could be 0, 1, 0, 1, 0. And then you'll have some more framing bits. And this might be 2 stop bits. As the 2 stop bits come in, it's 1, 0, 1, 0, 1, 0. So you want to set, this is your payload. The start bit and the 2 stop bits are your framing bits and your synchronizing bits. These 2 signals coming together allow you to resynchronize the clock internal in your receiver. So your asynchronous communication interface adapter, which could in theory be built into your CPU, is effectively looking for these 2 pulses to come together so it can determine the timing. Because the most important thing that you must have here is a regular sampling signal that comes in, let's say, in the middle. And this pulse that comes in is going to shape when your little D flip-flops are going to latch the bit and put it into a shift register. So your goal in taking serial communication bits that are coming in 1 bit at a time is to do a serial to parallel conversion. So you shift them in using your sampling clock and to a shift register and then present them in parallel to the computer. So if I give you 1, 0, 1, 1, 0 in sequence, what I want to do is go into a shift register with a shift input and then output 1, 2, 3, 4, 5 bits. And when they're done, and I'm about to hit the stop bits, I want the microcontroller to grab those bits and put them into a register which gets stored in memory somewhere. Perhaps you're sending strings off to your computer from your serial port. So this goes in marching along 1 bit at a time. So it comes out in parallel, and the microcontroller is signaled that these bits are ready, and it takes those bits and pushes them into a stack, or throws them into an array, or does whatever it's doing with serial data. And you see this all the time when you open up the serial monitor on your Arduino IDE. Right? That's a critical task. So I've got framing bits, start bits and stop bits. I've got data bits, and oftentimes I'll do something like this. I want a serial port with 8, none, 1. 8 data bits, no parity, perhaps 1 stop bit and 1 start bit. If that's the case, then I've got 2 bits that are just being used to frame and synchronize the receiver. And 8 bits worth of, I will call it payload. So if I take my payload, that's the data, and divide by the data plus the overhead, which is 2 bits plus 8 bits, then it's going to give me 10 in the denominator and 8 in the numerator, then I'm going to have the utilization of the system. I can express that as a number that goes between 0 and 1, or I can express it as a percentage if I multiply by 100. So oftentimes when we do something like put in a parity bit or an extra stop bit, we're harming the utilization, but maybe we're increasing our communication reliability, which might actually be a good trade-off. Yes, sir.
Is that different from the duty cycles? Or something else?
That's not duty cycles.
Completely different.
Totally different. Utilization is directly linked to performance. I can find that the best performance I get when I get to work, when I want to go to work, is when nobody else is on the road but me. Right? COVID, everybody's home, right? I got the whole I-95 to myself. I can go as fast as I like. I'm not stuck in traffic. Nobody's using I-95. When utilization is low, performance is high. Consider, for example, the overhead of a pair of sneakers. A pair of sneakers could weigh, I don't know, make up a number, 2 pounds. You could weigh maybe 150 pounds. So 150 over 150 plus 2, utilization is almost, I don't know, almost 100%. Now let's assume you're going to ride around in your car, and your car weighs a little bit more than 2 pounds. It weighs 2 tons. Now you got 150 pounds divided by 150 pounds plus 2 tons. Now your utilization is way low. But when you're in your car, you're moving 2 tons around at 60 miles an hour. Your performance is great. So what we want to do is we want to compare utilization and performance in various different things. I could do this with the Saturn V rocket. Your payload is 3 astronauts. But what's it weigh? Like 1 million pounds? Holy mackerel. But that's what it takes to get to the moon, right? You can't do that with sneakers. So as a result, we see utilization has application in all kinds of areas other than communication systems. I think that's all the time we have for today. We'll pick up homework 2 next time, and I'll have released it by then. Stay safe. Thank you.
Can you tell me what those D's and the H's stand for?
What does the D and the A stand for? Here, the D is the data. H is your header. And this is U for utilization. Sure. And this recording. Yes, let me just end the recording. How do I end the recording? Stop.